Today we're going to be talking about how to approximate the area under a curve using left, right, midpoint, and the trapezoid method. The first method we are going to use to approximate the area under the curve of y equals f of x is to use left endpoints. We're going to use n number of rectangles, and we're going to look at the interval from a to b. The area under the curve y equals f of x can be approximated by finding the area of individual rectangles. The width of the rectangle can be calculated by doing b minus a over the number of rectangles. And the height of the rectangle can be calculated by finding the y value at the left endpoint of the rectangle. To find the endpoints of the rectangles, you start with a equals x sub 0, and then the next endpoint will be x sub 1, which is equal to x sub 0 plus delta x. Now, to approximate the area under the curve, you find the area of the individual rectangles. So the area of the first rectangle would be f of x sub 0, which is the height at the left endpoint, times delta x, which is the width. The area of the second rectangle would be f of x sub 1 times delta x, and so on, until you get to f of x sub n minus 1 times delta x, which is the area of the last rectangle. It is important to note when you're using left endpoints, you do not use f of x sub n. Sigma notation can be used to provide a general formula to find the area under a curve using left endpoints. However, it is important to note that this is an approximation, and when you have a function that is decreasing and you're using left endpoints, you will get an over approximation because of this extra area being added. However, when the function is increasing, you will have an under approximation. When using right endpoints to approximate the area under the curve of y equals f of x, the width will once again be b minus a divided by the number of rectangles. However, the height of the first rectangle will be f of x sub 1 instead of f of x sub 0. The approximated area under the curve will then be f of x sub 1 times delta x plus f of x sub 2 times delta x, all the way to f of x sub n times delta x. Once again, this can be represented in sigma notation. However, unlike the sigma notation for the left endpoint, the sigma notation for the right endpoint is just f of x sub I times delta x. A useful trick is that if delta x is the same, you can factor out delta x and add up all the heights and then multiply that by delta x. When using right endpoints to approximate the area, when the function is decreasing, the approximation will be an underestimate. However, when the function is increasing, the approximation will be an overestimate. Next, we're going to use midpoints to approximate the area under y equals f of x. The width will once again be delta x, which is going to be b minus a divided by the number of rectangles. However, the height will be determined by using the midpoint between x sub 0 and x sub 1. So the approximated area would be f of x sub 0 plus f of x sub 1 divided by 2 times the width for the first rectangle. For the second rectangle, the height will be x sub 1 plus x sub 2 divided by 2 times delta x, the width. So you're basically just finding the midpoint and then finding the y-coordinate that goes along with that midpoint. Once again, the area can be represented using sigma notation, where you have f of x sub I minus 1 plus x sub I divided by 2 all times delta x. A common mistake that students will make is that they will think that the average area calculated using left endpoints and right endpoints will equal the midpoint. However, that is not true. The next method to approximate the area under the curve is using trapezoids. The formula for the area of a trapezoid is base 1 plus base 2 times height divided by 2. The first method that you can use trapezoids to find the area under the curve is to find the area of each trapezoid individually. The area of the first trapezoid would be base 1, which would be f of x sub 0, plus base 2, which is f of x sub 1, divided by 2 times the height, which would be delta x. The same process can be done for each of the trapezoids, and to find the total area, the areas of each trapezoid will be added together. The second method that can be used can only be used if delta x is equal, and that the height of the trapezoids does not change. The general formula for this method is f of x sub 0 plus 2f of x sub 1 plus 2f of x sub 2 all the way to 2 times f of x sub n minus 1 plus f of x sub n. It is important to note that the first term and the last term are not multiplied by 2. This whole thing is then multiplied by delta x divided by 2. So in this case, you would have f of x sub 0 plus 2f of x sub 1 plus 2f of x plus 2 all the way to just f of x sub 7. Now we can do a practice problem. The problem is estimate the area between f of x equals x cubed minus 5x squared plus 6x plus 5 and the x-axis using n equals 5 subintervals. So things to note is that the graph is positive and the width of each subinterval will be b minus a divided by the number of rectangles, which is 4 minus 0 over 5, which is 4/5 or 0.8. If you want to find the area under the curve using right endpoints, we can start by multiplying the width times the right endpoints, which would be f of x sub 1 all the way to f of x sub 5. You can then plug in the heights, which we can figure out by looking at the graph, add them together, and we should get 28.96. The area can also be approximated using left endpoints, and in this case, we will start with f of x sub 0, which is f of 0, all the way to f of x sub 4, which is 3.2. Once again, the y values can be calculated by looking at the graph, and when you add all the values, you will get 22.56. Another way to calculate the area under the curve would be using the midpoint method. The midpoint can be determined by adding f of x sub 0 plus f of x sub 1 and dividing it by 2. This can be done for each rectangle and multiplied by the width.
Okay, now it's time to do a trapezoid practice problem, or a TPP. Let's review the trapezoid rule. The trapezoid rule says that you have to take the length of the subinterval, take it over 2, and then multiply it by this in the middle. And then we'll review why these y values of the subintervals in the middle are times 2 and why these on the ends are just times 1. So the question asks, using 4 subintervals, evaluate this integral from 0 to 2 using the trapezoid rule. And so the first thing that we have to do is determine what this value is, what this delta x is. And then we see that this delta x, because on the interval 0 to 2, you take that over the number of subintervals. So it's b minus a over the number of subintervals, which is 1 over 2. And then we put that into the trapezoid rule. So we have 1 over 2, which is exactly how it's drawn over here, 0.5, over 2, because that's the trapezoid area formula. And that gets you 1/4. And then you multiply it by this in the middle, this equation in the middle. And so what you end up getting is 1 over 4 times, and then you plug this in, you plug 0 into this equation, so it's e to the 0 squared plus e. 2 times, you have to remember this 2 for every single one except for this at the end. So 2 times e to the 1 squared plus 2 times e to the 1.5 squared. It's just times 1 on that. So it's e to the 2 squared. Okay, and so when you plug that in, you get 1/4 times 82.59. And then that turns out to be 20.64. And so the actual value of the area under the curve is 16.45. Okay, that's the actual area. But because we're drawing trapezoids and we're connecting these, this graph is concave up. So what we're going to see is we're going to overestimate the area every single time we draw a trapezoid. We're calculating each of these trapezoids individually. And so each of these trapezoids has a height, but this trapezoid over here and this one over here share this base. And so we have to use this twice. And because this one and this one do not have a shared base, they were just multiplied by 1.